So welcome to week 6 of Specialist Maths, and week 6 we're covering complex numbers, or we're introducing complex numbers. So hopefully you've seen these before. So complex numbers, building on all the numbers that you've learnt about so far, just adding another set. The human mind is very inventive. So these first came about, supposedly, first documented evidence of them was in 1545. And an Italian mathematician, Cardano, proposed that this was true. This is the difference of products. Can you see? So you're able to make 40 equal, open bracket 5 plus square root of negative 15, open bracket 5 minus negative square root of negative 15. It's funny. So this is the first time that complex numbers were documented, or first documented evidence of them in mathematics. So in effect, this Cardano mathematician is proposing that the square root of negative 15 can be found. It's actually an imaginary number, so it's equal to the square root of 15I squared. Now this is a special leap forward. There he is, big leap forward, and the invention of this concept that there is an imaginary number, when you square it, you get negative 1. And that imaginary number is represented with a lowercase I. So this is the whole basis of complex number theory. When we talk about complex numbers as a set, we use the letter C to represent the complex numbers, uppercase C. You've already seen how real numbers are represented with an uppercase R, so we're just extending our sets. So we've got the set of C, the complex number set, as well as the real numbers. So we've got this beautiful little concept now of imaginary numbers. I squared is equal to negative 1, which makes it possible to take the square root of negative numbers. Who knew? Okay, so this is imagination gone wild. Very imaginative. So we've got, if we can work out the square root of negative 25, for example. If we express negative 25 as 25I squared, then we can actually find the square root as a imaginary plus minus 5I, and we can do that with any negative number. We have these beautiful patterns emerging when we do raise this imaginary number to different powers or different indices. Like all numbers, raising any number to the power of 0 is equal to 1. Raising any base to a power of 1 is equal to the number itself. It starts to become interesting here. So you notice a pattern. I squared is equal to negative 1. I cubed is equal to negative I. Then we've got I to the power of 4 is equal to 1. And then this pattern repeats again. So we've got repeating. I5 is equal to I squared is equal to I6. I3 is equal to I7, etc. And it repeats this way infinitely. So it's, have I got everything? And then it just repeats again. Okay, so you can see here we've got this pattern emerging, and we can actually use that to inform us what's going to happen to certain kind of complex numbers when they're raised to certain powers. Okay, so a complex number can have a real and an imaginary part to it as well. And the real parts are, as we understand them, they're just real numbers, and the imaginary part involves that symbol I. So here are some examples. So we have 4 plus 3i. This is a complex number. The real part of it is the 4, and the imaginary part of it is the 3, just the coefficient in front of the I. The next number along, negative 4i, has 0 as its real part, and its imaginary part is negative 4. Similarly, real numbers can be expressed as complex numbers. So 5 plus 0i, you might know that in everyday life it's just 5, has a real part equal to 5 and an imaginary part is equal to 0. We have this other notation as well for talking about real parts of complex numbers. This RE. RE is a function. If you pass in a complex number, it should return to you the real part of that complex number. So in this case, if z is equal to negative 1 minus I, the real part of z is negative 1. Imaginary is another function, im for short, which takes the complex number and returns the imaginary part of the complex number. So if you pass z into the imaginary function, it should return you -1, which is, in this case, for this particular complex number. And you can use that throughout, so you can do it to any complex number. You can have another complex number, z is equal to -3 plus root 7i. The real component of that number is -3. The imaginary component of that number is root 7. And it can even be expressed algebraically. So you can have z is equal to x plus 3 plus open bracket 2y minus 5 of I. Again, the real functionality passing in that complex number should return the real part of that number, which is x plus 3, and the imaginary part of that number is 2y minus 5, the coefficient of the I, the imaginary component. Okay, so that's just some terminology that you have to become aware of. And when we're graphing these, we normally use an Argand plane where the horizontal axis represents the real component, and it's often labelled with an REZ, so that's the real component of the complex number, and the vertical axis, which corresponds to the y-axis, is used to show the imaginary part of the complex number. So here are some examples. Here we've got 4 plus 3i, 4 units in the real and 3 units in the imaginary. So it's the equivalent, I suppose, of this coordinate that you might be familiar with on the xy plane, 4, 3. This one over here in the second quadrant is -3 plus 2i. -3 is the real component, 2i is the imaginary component. Okay, so that's just some terminology there. So we've got all of that and more. Okay, so when we're adding and subtracting complex numbers, it's pretty easy. It's just treat it like an algebraic expression. You add like terms with like terms. You add the reals to the reals and the imaginaries to the imaginaries. So in this example, we have a complex number z1 and z2 with different components. z1 is a plus bi, z2 is c plus di. When you add them together, you add the like with the like, the real with the real, and the imaginary with the imaginary. Same when you're doing subtraction. You subtract the real with the real and the imaginary with the imaginary. Why is the real on the x-axis and the imaginary is on the y-axis? Shagmin, I don't know why. I don't. Somebody made up that system of representing. That's like a convention. So in this example, let's have a look. There's two complex numbers being added together. Pretty simple. 4 minus 6i in brackets, that's one complex number being added to -3 plus 7i. So we can just see here we're just adding the real to the real and the imaginary to the imaginary. You're just treating I almost as a polynomial variable, and we end up simplifying the answer, and that's the result. And here's a subtraction example. 10 minus 4i, take away 5 minus 2i, subtract the real from the real and the imaginary from the imaginary for the final answer. Exactly right, Fletch. That's one reason as well. It matches up with the trigonometry. So the trigonometries come first, and then the complex, the Argand plane, has been related to the circular functions in the unit circle. Fletch is onto something there when he's talking about e to the power of is it I pi. This is a definition that you might like to Google, which is also, as we know, that's equal to I squared. It's also equal to -1. Okay, so but we don't need to know about the numbers in this exponential form, but you might like to find out about them. It is super interesting, Fletch. You're absolutely right. Super interesting. Okay, so let's have a look how we do multiplying. Yes, Amanda, it is. It's very famous. It's a very famous equation. You can Google it later. It's not part of the specialist maths course, though. I wish it was, because it's kind of nice, but it's not. Okay, so let's have a look at the multiplication as well. So the multiplication, I think I've got this example here. So we're multiplying out two brackets, just like you would when you're doing an expansion here of two brackets. whatever you want to call it, the FOIL method, whatever you want to call it. You just multiply all the terms out. So that's 2 times 3 plus 2 times 5i minus 4i times 3 minus 4i times 5i. Okay, and then you simplify all the terms. So we're going to end up with this next step, that's simplifying the terms, but hey, you need to remember that I squared is equal to the minus negative 1. So whenever we see that, we need to further simplify that. So then we can continue on and simplify the final expression. Okay, is that clear? That example okay? So just basically expanding the brackets, looking for I squareds that result, or other powers of I that we can simplify. Because remember, even other higher powers, I cubed is simply just I squared times I. Okay, all of that stuff. We need to remember all our index laws. Okay, so here's another one, just squaring, binomial expression, 7 plus 3i all squared. We all know how to do that. Square the first term, 2 times the product of the 2 other terms plus the last term squared. So we could simplify this. We're going to get 49 plus 42i plus 9i squared. Replace the I squared with a negative 1 and keep on simplifying this expression. Okay. So if I now talk about, if I do this, what's the answer? If I put this function RE around this complex number, yes, the answer is 40. And if I put im around the same, what's the answer? 42. Yep. So you're on top of that notation. Okay, so let's keep going. Division. Now division is slightly different. We divide in a special kind of a way for complex numbers. We actually use a thing called a conjugate, which I'm going to explain. So if we have a complex number, any complex number can be represented with a real and an imaginary component. So z is equal to x plus yi. The conjugate is simply shown with this little flat sort of line above the complex number. That just swaps the sign to the opposite sign between the real and the imaginary component. So it just changes it to the opposite sign of addition or subtraction. And then we can work out the product. It has special properties. The product of a complex number and its conjugate is always a real number. That's something we can actually show. So if we have any complex number, like z is equal to x plus iy, we can just work out the conjugate is just a reflection in the real axis. So by changing that expression in between the real and the imaginary part to the opposite sign, you can just see it's just reflected in the real axis, and this angle it makes is going to be the same as that angle, with the one positive angle theta and one negative angle theta. It's the same angle because it's got the same lengths. This is y here, that's negative y, and we have x here. Okay. So that's an interesting property. If we multiply those two together, even if you do it yourself, you'll see that you end up with a real number. So if you just do the algebra yourself here, x plus yi, x minus yi, that's a difference of, you're going to end up with what? You're going to end up with x squared minus y squared, I squared. Agree? Which is going to end up being x squared and I squared is equal to negative 1 plus y squared. Is that okay? Just by doing the algebra. So that's a handy way. So the conjugate of a complex number is used to divide, and it's used to make denominators real. For some reason, when we're doing complex number arithmetic, we want the denominators on fractions to be real. I don't know why. Somebody made that rule. We just got to stick with it. Okay, so there's those conjugates there. Okay, so we've just seen that. So we can, by multiplying a real by its conjugate, we end up with a real product. So let's just see some examples here. So how it's used for division. So say we've got 5 plus 3i divided by 2 minus I. So we use the conjugate to do the division. So you can see here the conjugate is applied to both the numerator and the denominator. In effect, it's multiplying it by 1, which we know still makes it the same fraction. But now we can actually make the denominator a real number. By just multiplying these brackets out, we can simplify and see that the denominator now becomes 5. So we can express this division. The result of that division is equal to 7/5 plus 11/5 I. And we might say something like this: the product of the complex number with its conjugate is a real number. Okay, so this is in mathematical notation describing what will happen and why we use it for the division here. Okay, we end up with a real. Okay, so we'll talk a bit about the Argand plane too, which is an interesting place to go, because the way the multiplication works on complex numbers has really interesting geometric properties that we're going to look at. So here's the Argand plane. We just talked about that earlier, how the real component is equivalent to the x-axis and the imaginary component of a complex number is equivalent to the y-axis. So let's have a look here, some examples. Z1 is equal to 3 plus 2i. So in this animation we'll see where these go. So this is 3 units in the real and 2 units in the imaginary direction. So that's where Z1 is. 3 units in the real, 2 in the imaginary. Okay, Z2, here's another one, -2 plus I. So this is -2, that's in the second quadrant, right there. Okay, so that's interesting. Okay, we can add them together, Z1 plus Z2. So we can get a result there. We just add the reals to the reals and the imaginary to the imaginary. And we end up with this result right there. Okay, so that looks really interesting, doesn't it? I don't know. Sort of like adding vectors too sometimes, isn't it, a little bit? We can multiply 2 times Z2, that's just scaling that up, that's going to be -4 plus 2i. Where is it? Just right there. Okay. What else can we do? We can take the conjugate of a number. So we're going to take the conjugate of Z2. This is Z2 here. So that's just going to reflect that number in the real axis. So it's going to go here in the third quadrant. And what else have I got? And then the conjugate of the addition that we just did up here. The conjugate of that looks really complicated, but it's just the notation can make it look more difficult than what it actually is. You just have to learn what the notation means. That's the conjugate there, so that's going to be a reflection of this point in the real axis. So right there. It's just very interesting the way that all works. Okay, so another interesting feature, when you multiply any number by I, that imaginary number, it rotates that number 90 degrees anti-clockwise. If you multiply by -I, you end up rotating the number 90 degrees clockwise. Another interesting feature. And it kind of goes back to what Fletch was saying before about this being related to circular functions. So let's have a look at that happening. So if we have a very, very simple real number or complex number, there it is. I'll just make it a Z1 is equal to 1 plus 0i. So Z1, summation mix, okay, is going to be right there. Okay. Now, if we multiply Z1 by I, it's going to rotate this clockwise by 90 degrees. I times Z1, that's going to equal I. That right there, see how it rotated the number? 90 degrees. Now if we multiply it by I again, what happened there? What happened there? So this is multiplying it by I again. Oh no, it's not. Okay, I'm doing the negative one now. I thought I was going to multiply it again. Okay, so let's just do it by negative I times Z1. It should rotate 90 degrees clockwise this time. You're going to see that's about to happen. So there you go. So we've got this, this was multiplying by I, and this was multiplying by negative I. Oops. So it's quite an interesting property. And if you keep on multiplying by I, you can keep on rotating all the way around, either clockwise or anti-clockwise. It's quite an interesting property there. Okay, so let's do it with a little bit of a trickier example. So we've got Z1 this time, another complex number is equal to 3 plus 2i, just shown there. If we multiply that by I, it should rotate that number 90 degrees anti-clockwise. So let's do that. So you can see when you do that, all you're doing is turning the real component into the imaginary component, and the previously imaginary component now becomes a real component. So multiplying I by Z1 ends up with 2i squared, which simplifies to be, because I squared is equal to negative 1, that simplifies to be negative 2 plus 3i, and voila, if we graph that, you see a lovely 90 degrees rotation thing happening here, anti-clockwise. Okay, that makes sense? And if we do it by negative I, it should go 90 degrees anti-clockwise. So negative I, so multiply, that's going to be negative 3i plus negative I times 2i, which is going to give us 2 minus 3i, simplifying that one out, which ends up being over here, which is a rotation clockwise. Okay, it's kind of a very, very nice attribute, interesting property, which brings us to talking about polar forms. So far we have talked about complex numbers with real and imaginary components. So we have these real and imaginary components. But we can also describe them in a different way. We can describe them with a magnitude and an angle, which is in essence what a polar form is. This is the magnitude of the number, that's how big it is, and this is the angle it is relative to the real axis. So let's see an example of that. And there's some more notation to learn, even more notation and more terminology. So if we sketch any complex number in an argand or complex plane, we know that it's got, if it has real components, we put them on the real axis. If it has imaginary components, we put them on the imaginary axis. But we can work out for that number what is its magnitude or its distance from the origin, and we usually use the letter R to represent the distance from the origin, or this symbol modulus of Z, which just means the magnitude of Z, I suppose, if you like, the modulus part, the real, just the measure of the number, its magnitude really. And then argz is the principal angle of the number. And so what does that look like? So you've got, you know, from the unit circle, you can work out any exact value if you know it, or you can work out a value on the unit circle. Similar kind of principle, except the radius of the circle can be any radius. So we can represent x plus iy as a distance from the origin and an angle relative to the real axis. And it's the same number we're talking about. It's the same complex number we're talking about. Just refer to it in a different way. We can work out the distance from the origin by using old Pythagoras. Gee, he's so popular. and we can work out the angle by using tan. Tan is the rise over the run, and then we can just adjust the angle to make sure it's in a particular domain we need to look at in a minute. So I'm pretty sure you can do that with your old SOHCAHTOA. You've got your X and your Y. Whoops, your X is your real component and your Y is your imaginary. You can easily work out what that angle is. Okay, this is the domain we need to restrict our angle to, because you know angles, they go on forever and ever. We have to restrict when we're talking about the argument of a complex number. We're actually talking about the angle it makes with the real axis, and it's actually restricted. Our answer must be restricted to be within this domain, not including negative pi and pi inclusive. So what does that mean? It goes from here, but doesn't include negative pi, to pi. Oops. That makes sense. That is how we have to express the final answer for an argument of a complex number. That's just a rule. Okay, so let's have a look at that again. And we have to keep in mind all the exact value ratios that we learnt about in our circular functions. We still need to know those. And how do they relate to arguments, for example. So, okay, so we need to know those. So we've got all the different angles here labelled: pi on 6, pi on 3, pi on 2, 2 pi on 3. These are going, I guess they're going anti-clockwise. And also the argument is anti-clockwise as well, but it starts from negative pi, and goes anti-clockwise. It has like a different reference point, if that makes sense. So that would be negative pi there, and then it would be negative 5 pi on 6. That would be the argument here. Negative, am I going right? This still will be 0, then pi on 6, pi on 3, pi on 2, that's correct. Etc. to pi on 3. Just trying to put the arguments on. 5 pi on 6 for around the unit circle. So that would be negative 5 pi on 6, negative 4 pi on 6, negative 3 pi on 6. Simplifying it, of course, you need to simplify it. Negative 2 pi on 6, negative pi on 6. So in green I've put on the argument equivalents of those angles, if that makes sense, because the argument needs to be restricted between, but not including negative pi to pi. So that's a really important thing when you're giving your final answer. You need to make sure you're in that correct domain. So we work out the complex number can be represented in Cartesian form as z is equal to x plus iy. Sometimes that's called rectangular form, or it can be expressed in polar form. And this is just short, this cis is just short. Cis theta is shorthand for cos theta plus I sine of theta. This is where you get that's what cis theta is. Cis theta. And if I underline those different bits, you can see that you get your cis here from the cos, the I, and the S. So that's just short for that. And if you look at this, the components here, this bit here, this x part, that is the equivalent of cos of theta. That distance there is the x part, and this distance is the equivalent of r sine of theta. So we can express in Cartesian form or in polar form, it's the same number. That makes sense. Except in polar form we talk about the angle and the distance from the origin. But it's in essence the same thing. Okay. because x is equal to r cos theta, y is equal to I sin theta. So x plus yi can be expressed as r times cos theta plus I r times sin theta. See? And then that is abbreviated to make this new little expression that we need to learn. R cos theta, I sin theta is shorthand r cis theta. Some more new terminology for you to make sure that you understand when you're reading and apply. Okay, so this expression, it's written in longhand, but here it is in shorthand, is called the polar form of a complex number. So you can have a polar form or a rectangular or Cartesian form. Gross. I don't know what gross is. What do you mean? And of course I've just reiterated that several times. So get used to looking at that. Okay, so finding the modulus. Here we go. Here's an example. Here's a Cartesian form of a complex number, minus 1 minus I. So we've got to find the modulus. Pretty simple. We're just going to use Pythagoras' theorem. If we looked at where this was on a Argand plane, it's the real bit and the imaginary part. It's negative 1, negative I. So it's here. That number is right there. So we've got to work out how to express that in polar form. So we need to work out the distance from the origin, which is negative 1 squared plus negative 1 squared. Just applying a bit of Pythagoras' theorem to work out that the modulus, the distance from the origin, is root 2. Okay, so then we can work out the angle. We can see that it's just going to be a pi on 4 type of angle, but we've got to make sure we express it correctly as an argument in the correct interval, in the correct domain. So we know that that angle there, we can express it, we can talk about it being equal to 5 pi on 4, but that is not correct, because remember the argument needs to be expressed to be between negative pi and pi. So we need to adjust that, and that becomes equivalently expressed with the argument or the angle negative 3 pi on 4 is the equivalent of 5 pi on 4, but argument needs to be restricted into that interval, negative pi and pi. Can you see that? And so then we can express the rectangular form of the complex number in polar form, and we can still find it's exactly the same number. Okay, it's the same number. Here it is right there. Just got two identities. It's got the rectangular Cartesian form identity and the polar form identity. When we have a number in polar form, some operations, arithmetic operations, become far easier. So uppercase arg has to be restricted within that domain. I don't know, technically speaking, I would only use uppercase arg. I wouldn't talk too much about lowercase arg. I would just use uppercase arg and make sure I finally give my final answer in the correct domain. Why do we use polar form? Because it makes multiplication and division easier for complex numbers. So if we put a number into polar form, so we have, I think I've made a typo here. That should be Z1 equals and Z2 equals. So if we've expressed, got two complex numbers expressed in polar form, so when we multiply them, it becomes really easy. We just multiply the moduluses by the moduluses, and we just add the angles. We add the angles, the arguments. How does this look? It looks like this. And then we simplify, we make sure that the final answer, the argument is in the interval negative pi to pi, by using symmetry and all sorts of other properties of angles that we know about in a unit circle. Okay, so let's see one in action here. So say we had 4 cis pi on 2 times 2 cis pi on 4. Okay, what is that? 4 cis pi on 2. Well, that's basically 4 cis pi on 2 is basically up here. That's 4i. And 2 cis pi on 4. That means that so one number's up here, and the other one has a modulus of 4, and the other one has pi on 4. Okay, just trying to draw what's going on here. Let's multiply them together according to the rules we just saw before. So when you multiply two complex numbers in polar form together, you multiply the real component by the real component, and then you add the arguments together. So you end up with, in this case, 4 times 2 is 8 cis 3 pi on 4, which is fine because that's fine. That argument is in the interval that we're happy with. So this number is in the second quadrant, the modulus is equal to 8, the result and the argument is equal to 3 pi on 4. And we can re-express that number in rectangular form or Cartesian form by expanding that cis to what it really means. Remember, cis is just shorthand for cos of the angle plus sine of the angle times I. And then we can expand that. We know our exact values, 3 pi on 4, that's in the second quadrant. Cosine is negative in the second quadrant. Sine is positive in the second quadrant. And then we can simplify this expression. And we've turned the polar form back into the rectangular form. Okay, we can go either way because they're all just related around that origin there. Okay, again, this is a bit of a typo here. That should be Z1 equals R1 and Z2. So now we're going to do division. So division is also simplified when we use polar form. So if the modulus is not equal to 0, we can do this. So when we're dividing R1 cis theta 1 by R2 cis theta 2, we just divide the moduluses by each other and we subtract the angles. So we can write this in compact form. R cis theta 1 divided by R cis theta 2 is simply the moduluses divided and the arguments subtracted. Makes it so much easier. So much easier. So that's important. So if we keep that in mind, we can do an easy division here. So here we've got one I made up earlier, 16 cis of 7 pi over 18 divided by 4 cis 2 pi on 9. Divide the moduluses, subtract the arguments. And here's our final answer. Whoops, still working on our final answer, simplifying our final answer, still simplifying our final answer. Okay, that looks a lot nicer, doesn't it? And it's a lot simpler to do than to do in rectangular form. And we might be asked to express the final solution in rectangular form. Okay, so if we did this in, yes, just showing you how to get it in rectangular form, pi on 6 is one of our exact values that we should know about. 4 cis pi on 6 is the same as 4 times cos of pi on 6 plus 4 times sine of pi on 6 times I. Put in those exact ratios. This is in the first quadrant. This is a first quadrant number. Okay. All okay? Now, usually we work with radians, but sometimes you might see this occurring as well. You might see the argument expressed in degrees. Same rules apply. You divide the moduli, and you subtract the angles. Okay, so you divide the moduli and subtract the angles. Okay, but it's not often, we don't often deal with degrees with complex numbers. They usually are dealing with radians at all times, but hey, I don't know. You might see this, you know what to do. Okay, so we've got this magic imaginary number Now, not only can we factorize in the real domain, we can factorize in C, which is in the complex domain. So we can find a lot more solutions. So for example, here's one that you might not have been able to solve in the real domain, but hey, guess what? You can solve it in the complex domain. X squared plus 4 is equal to 0. Like normally, when you draw this graph, right, it looks like that. If you draw this parabola, in the real, it doesn't have any solutions. It's never equal to 0 in the real. But in the imaginary it is, because we can use this special property, this special imaginary number, I squared equals -1, to factorize this. So this can be re-expressed, x squared plus 4 can be re-expressed as x squared minus 4i squared. So we can now make that equal to 0, and this will be a different perfect squares now. So we can factorize the left-hand side, and we now have two complex solutions for this particular problem, which, as Marco has correctly pointed out, is 2 plus minus 2i. So we're going to use that to keep on factorizing polynomials that we weren't able to factorize before in real. Now you've got to be careful of this. To be able to do factorization in the complex number system, it needs to actually ask you for that. So it's actually saying where x is in the complex number domain. So that means you can actually find complex solutions. In math methods, you will never get this. It will always say x is an element of the reals. So if we look at this particular parabola, and we sort of try and complete the square here to try and factorize it. We could have used the quadratic formula as well, but let's just humour me here. So we're going to make a perfect square there. So we've got to, and we're going to split this term 18 up into 16 plus 2. So you can see this can be expressed now. It doesn't look like we're going to get a difference of perfect squares here in a minute. So these first three terms can be also expressed as x minus 4 all squared plus 2. So we're going to put that I squared in there, and now we're going to get a difference of perfect squares. So we can now factorize this, and we end up with these two factors equal to 0, and you can see now we're going to end up with two complex number solutions for this particular problem. X can be equal to 4 plus minus root 2i. You could have used the quadratic formula on this as well. If we use the quadratic formula, what would we have gotten? We would have gotten x was equal to 8 plus minus, -8 squared minus 4 times a, which is 1, times c, which is 18, on 2 times a, which is 2. Now, in here is going to be, underneath the square root would be a negative number, but you know what you could do, whatever that negative number is. What is it? Anyone worked it out? What's a negative number under the square root in this case? It's 64 minus 4 times 18. What's that? Anyone got that one? What is that? 64 minus 4 times 18 times 18, blah, blah, blah. It's my calculator here. -8. Thank you, Timmy. So that's -8 over 2, which we know we can also express as equal to 8 plus minus 8i squared. And then we can simplify this, okay, as well. Okay, you fine with that? So you could have used the quadratic formula if you didn't feel like doing all this algebra. I wouldn't blame you one bit. Okay, so let's, okay. We're going to do more factorization in C next week. Okay, so this is basically the end of the lesson. But I just wanted to show you some fun things you can do with polar form numbers. And this bit's just for fun. It's not going to be on the SAC or anything. It's not going to be on the exam. It's just mucking around. But for those of you who like looking up things, playing around with your mathematics, you can actually make all sorts of interesting graphs using polar form numbers. So you can make a rose, for example. So let's have a look here. So here's a rose. R equals 3 sine of theta. So you can actually just change theta and you end up with all these lovely points here. When theta is equal to pi on 6, you end up with 2.6 pi on 6. That is 2.6 pi on 6 right there. When the angle is pi on 4, you end up with 3 pi on 4 right here. So if you join all these lovely dots, keep on going around, working out all those angles, you end up with this lovely, this particular one's a 4-petaled rose. Can you see? It's kind of fun. So it's kind of nice. It's not in the course, but it's kind of nice. I kind of like it. So, and you can get even more complicated. You know, make spirals as well. So here's an example of a spiral. So this is also a polar form number. R is equal to negative a half theta. So don't think am I filling these ones in? Don't think I have. I might leave this one for you to fill it in. But you can play around with that. No, they're not in the study design, Timmy, so you can switch off if you want. Just for fun. Okay, so I'm going to stop the recording now. Thank you everyone. If you want to explore these further, there's a whole heap of them. They're just for fun. They're not in the study design. Okay, thank you everyone. Bye for now.